Welcome back to the Deep Dive, where we take your sources and distill the most fascinating insights, making you feel instantly well-informed. Today, we're taking a journey into a cornerstone of calculus, a concept so powerful it unlocks understanding across science, engineering, even everyday life. The integral. We're digging into Chapter 5 of Calculus. Early Transcendental is a section that, well, it really unpacks the power of the integral, showing how it unlocks understanding in everything from physics to biology.
That's exactly right. If our previous deep dive into derivatives was all about, rates of change and tangent lines, today we explore its profound counterpart. This is the other central idea in calculus, and as the material we've reviewed puts it, it's all about this all-important relationship between derivatives and integrals. They are, in a sense, inverse processes.
Right.
Our mission today is to cut through any, let's say, perceived complexity, giving you clear, intuitive explanations, some practical examples, and hopefully those aha moments that make these abstract ideas click. We'll show you how finding the area under a curve, or maybe the total distance traveled, leads to some really surprising connections.
Okay, so to kick us off, let's unpack where this idea of the integral even comes from. The source material highlights two, well, they seem simple, but they're incredibly foundational challenges: the area problem and the distance problem. How do these questions lead us to such a big concept?
Yeah, that's a great place to start. Think about finding the area of a basic shape, like a rectangle or a triangle. Pretty easy, right? We've got formulas for that. But what about a region with curved sides, say the area under parabola? That's the area problem. It's about calculating the exact area of a region bounded by a function's curve, the x-axis, and maybe two vertical lines. The intuitive idea is there, sure, but getting a precise answer for that curve boundary, that's the real challenge.
And yeah, that sounds like something that could get overwhelming pretty quickly. How did mathematicians tackle something so complex?
Well, the ingenious solution, and it's detailed really well in our sources, is to approximate. And then refine that approximation infinitely. Remember how we used second lines to approximate tangent lines for derivatives?
Yeah.
Well, for areas, we do something similar. We approximate the curved region, the whole series of simple rectangles. Imagine dividing the area into these incredibly thin strips, okay? Then you approximate each strip with a rectangle, add up their areas, and then here's where it gets really interesting. You take the limit as the number of these rectangles goes to infinity.
Ah, okay, so as they get infinitely skinny.
Exactly. And the amazing thing is, these approximations consistently narrow in on the true area, no matter how, jagged the curve might be.
That's a really powerful visual. And how does this connect to the distance problem? Because on the surface, that feels like a totally different thing.
The connection is actually profound because it leads to the exact same underlying mathematical process. Imagine you're in a car, right? Your speedometer works, but the odometer is broken. If your velocity is constant, no problem. Distance is just velocity times time.
Simple enough.
But what if your velocity is constantly changing, like in any real drive? How do you find the total distance you've traveled? You do basically the same thing. You approximate the distance traveled in each tiny, tiny time interval by assuming your velocity was almost constant for that little burst. Then you sum up all those little distances.
Okay, so you're breaking time into little pieces, just like you broke the area into little pieces.
Precisely. The more often you measure your velocity, the more accurate your total distance estimate becomes. And it leads to the exact distance as the limit of these sums.
So whether we're talking about finding a curved area or figuring out distance with a changing velocity, the same special type of limit pops up. What's the big takeaway here, the aha moment?
The real aha is realizing that these two seemingly different problems, finding the area under a curve and finding the total distance traveled from a varying velocity, they lead to the identical mathematical structure. That structure is the limit of a sum of products. And this convergence, this realization that different problems share this structure, that's the foundation for what we call the definite integral.
Wow.
And it goes way beyond just area and distance. The material we reviewed mentions how integration solves problems involving, everything from volumes, lengths of curves, population forecasts, even analyzing forces on a dam or consumer surplus in economics. This abstract concept. Incredibly versatile, really powerful for modeling the real world.
That makes perfect sense intuitively. We're approximating, then taking a limit. Okay, now let's get a bit more precise. How does calculus formally define this limit of a sum?
Right, this leads us straight to the formal definition of a definite integral. You'll typically see it written with that elongated S symbol, the integral sign, from limits a to b of fs dx. That elongated S, which Leibniz introduced, is key because, as we learn from the text, an integral is fundamentally a limit of sums. Specifically, these sums we call Riemann sums, named after Bernhard Riemann. That whole notation just encapsulates the process, summing many infinitesimally thin rectangles or tiny increments.
And what does the number you get from this integral actually represent? Is it always just a positive area, or is there like a catch?
Not always, and this is really crucial. If your function, fx, is always positive on the interval you're looking at, then yes, the definite integral is exactly the area under the curve. But, and this is a big but, if fx dips below the x-axis, if it takes on both positive and negative values, then the definite integral represents the net area. That means it's the area of the regions above the x-axis minus the area of the regions below the x-axis. It's a difference of areas, not just a simple sum. So the result could actually be negative.
Ah, I see. So a negative result means there was more area below the axis than above it.
Precisely. It's about the net accumulation.
That's a great distinction. It's not just area, but net change in area in a way. And when can we be sure an integral actually exists? Like, when will this limit of Riemann sums actually settle on a single value?
Yeah, good question. The textbook assures us that if a function f is continuous on the interval, or even if it just has a finite number of, say, jump discontinuities, then it is integrable. That means the limit of the Riemann sums will always exist, and it'll give you the same value no matter how you choose your sample points within each little rectangle, left side, right side, middle.
Okay.
And actually, for practical estimation, when you can't find an exact answer easily, the midpoint rule is often highlighted as being a very accurate way to approximate.
Okay, so we've built the intuition, we have the formal definition, but the real game changer, right? The thing the source material calls the unquestionably most important theorem in calculus is the fundamental theorem of calculus. It sounds like this is what really connects differentiation and integration.
That's exactly where the magic happens. The Fundamental Theorem of Calculus, or FTC as it's often called, it has two parts, and they beautifully link differentiation and integration. Part one deals with functions that are actually defined as an integral. Think of a function, let's call it gx, that represents the accumulated area under another function, ft, starting from some fixed point a up to a variable point x. You can sort of picture gx as an area so far function.
An area so far function.
Exactly.
Okay, and what's so special about this gx?
The theorem, part one, states that if the original function f is continuous, then the derivative of this area so far function, gx, is simply the original function fx. Yeah. In plain language, if you define a function by integrating another function, and then you differentiate that new function, you basically get the original function right back. It's an incredible revelation. It really shows the deep inverse relationship between these two operations.
That's amazing, like undoing each other.
Exactly. The sources mention the Fresnel function, used in optics and highway design, which is defined by an integral. FTC Part 1 immediately tells us its derivative is just the sign part inside the integral. It makes analyzing some complex functions much easier.
That truly highlights the inverse relationship. So Part 1 gives us this amazing conceptual link, but for actually doing calculus, for calculating these integrals without going through that whole limit of sums thing every time, what's the key?
Ah, precisely.
Yeah.
That's part two of the fundamental theorem, and this is the computational powerhouse. Part two states that if you can find any antiderivative of your function, f, let's call it f, meaning if you differentiate f, you get f back.
Okay, an antiderivative.
Then the definite integral of x from a to b is simply fb, fa.
Yeah.
Just evaluate the antiderivative at the endpoints and subtract.
Wow. So no more limits of sums.
No more limits of sums. Remember that area under y, IC2 from 0 to 1 we talked about?
Right.
The one we approximated and said converges to 13?
Yeah, with the rectangles.
With FTC Part 2, you just find an antiderivative by 2. A simple one is 13 by 3. And you calculate f1 minus f leaves. So 13, 1, 3 minus 13. 3, that's just 13 minus 0, which is 13. Instantly.
That is revolutionary, seriously.
It absolutely was. It transformed calculus. It made previously incredibly challenging problems accessible to, well, anyone who could find an antiderivative.
Yeah.
It turned calculus into a systematic method.
So Part 2 makes evaluating definite integrals much more efficient. But that hinges on finding those antiderivatives in the first place, right? That seems like the key step now.
Exactly. And that's where indefinite integrals come into play. These are the ones written with the integral symbol but without the limits a and b, like integral fx. This notation represents the family of all possible antiderivatives of fx. And you always have to remember that plus c, the constant of integration.
Ah, yes, the plus c, because the derivative of any constant is 0.
Precisely. So there's always a whole family of functions whose derivative is fx. The textbook usually provides a table of common indefinite integrals, which are basically just our differentiation rules run in reverse. Like the antiderivative of xn is xn plus 1, n plus 1 plus c, as long as n isn't minus 1.
Okay. And how does all this connect back to real-world applications? We talked about area and distance, but this feels more fundamental.
It absolutely is.
Yeah.
This is where the net change theorem really shines. It's basically just a rephrasing of FTC Part 2.
Hmm.
Remember, FTC 2 says integral a to b fx a dx as a rate of change of some quantity f.
Like velocity is the rate of change of position.
Exactly. Then the integral of that rate of change gives you the net change in the original quantity f between a and b. So if vt is velocity, the integral of vt over a time interval gives you the net change in position, which is displacement.
Right, displacement. So if a particle moves forward then backward, the integral tells us its final position relative to the start, not the total ground it covered. That's still a key distinction.
Exactly right. Displacement is net change. If you drive to the store and come back home, your total distance traveled might be, say, 10 miles. But your displacement, your net change in position from where you started, that's 0.
Because you ended up back where you started.
Exactly. To find the total distance traveled, you had to integrate the speed, which is the absolute value of velocity. Speed is always positive or 0, so integrating it always accumulates the total ground covered. It never subtracts when you go backward. The textbook has examples showing a particle might end up, say, 4.5 meters to the left of where it started, negative displacement, but it might have actually traveled over 10 meters in total during that time, accounting for all the back and forth.
That makes the distinction incredibly clear. What are some other real-world rates where this net change theorem is super useful?
Oh, tons of them. Think about electric power consumption, PT. That's a rate of energy use, maybe in megawatts.
Yeah.
If you integrate PT over a full day, say from T0 to 24 hours.
You get the total energy used that day.
Exactly. The total energy in megawatt hours.
Yeah.
The units always work out.
Yeah.
Unit of the rate times, unit of time, or whatever the variable is. It applies to population growth rate, integrate that. You get the net change in population. Marginal cost in economics, integrate that. You get the total change in cost to produce a certain number of items. Water flowing into a tank at a certain rate, integrate the rate. You get the total change in the volume of water in the tank. It's everywhere.
That's really powerful. Okay, so finding antiderivatives is key. What happens when the function we need to integrate isn't immediately obvious from those basic rules, when things look more complicated?
Yeah, that happens a lot. That's where integration techniques come in. And the most fundamental one is the substitution rule. You can think of it as the reverse of the chain rule for differentiation.
Okay, the chain rule. That was for derivatives of composite functions like f, gx.
Right. The substitution rule helps when your integrand, the function you're integrating, looks something like a composition, maybe multiplied by the derivative of the inside part. The core idea is to simplify the integral by making a substitution. You let a new variable, usually u, equal the inside part, say u equal gx. If you choose u cleverly, the integral often transforms into a much simpler one involving just u. For instance, something complicated like integral by 3 cols by 4 plus 2 dx can become a simple 14 integral if you let u by 4 plus 2.
Because the derivative by 4 plus 2 is 4 by 3, which is almost there in the original integral.
Exactly. You handle the constant factor, and suddenly it's easy. It's a skill that definitely takes practice, figuring out the right u. And super important, if you're doing this with a definite integral, one with limits a and b, you have to remember to change those limits in terms of u as well. Or substitute back to x before plugging in the original limits.
Right, got to be consistent with the variable. And wasn't there also a neat trick for symmetric functions that sounded like a potential time saver?
Yes. A wonderful shortcut, definitely. It applies when you're integrating over a symmetric interval, like from a to plus a. If the function f you're integrating is even, meaning its graph is symmetric about the y-axis, like fx, you think by 2 or cos x.
Okay, like a mirror image.
Right. Then the integral from a to a is simply twice the integral from 0 to a. You only need to calculate half the area and then double it. Saves work. But even better, if the function f is odd, meaning its graph has rotational symmetry about the origin, like f dax x dax think by 3 or sen x.
Okay, where the opposite input gives the opposite output.
Then the integral from a to a is just 0. Always.
0, just like that.
Just like that. Because the area above the x-axis on one side perfectly cancels out the area below the x-axis on the other side due to the symmetry. This can save immense calculation time. The book gives an example like integrating tan x 1 plus by 2 plus by 4 from -1 to 1. That look horrible. But you check and realize the function is odd. So the integral, instantly 0. No calculation needed.
That is elegant It really shows how understanding the properties of functions pays off.
It absolutely does. These properties aren't just theoretical, they have practical computational benefits.
Wow. This deep dive into integrals has been truly illuminating. I mean, starting from just thinking about the area under a curve and ending up understanding these huge quantities like total energy consumption or population change or predicting motion. The integral is just this indispensable lens for viewing and measuring the world. It's pretty amazing how a concept developed centuries ago is still so incredibly relevant.
It really is a testament to the interconnectedness and power of mathematics. These concepts, hammered out by figures like Newton and Leibniz, they provide this universal language, a language for understanding accumulation, total change, and that crucial inverse relationship to rates of change.
Yeah.
The ability to model and solve these problems, connecting abstract theory to very real contexts in physics, engineering, economics, biology, it really all starts with getting a solid grasp of this chapter.
Yeah, what really stands out to me is how integrals give us this incredibly powerful way to add up infinitely many tiny pieces to find a meaningful total, whether it's actual physical area or distance traveled, or even more abstract things like accumulated cost or energy used over time. It feels like a shortcut to being well informed about accumulation. It makes you realize that these seemingly complex phenomena are often just the sum total of simpler changes, and integrals give us the tool to understand that sum perfectly. We really hope this deep dive has given you a clearer, maybe more intuitive picture of their power.
Thank you for joining us on this exploration into the world of integrals.
From the Last Minute Lecture team, thank you for diving deep with us.